Parallel robots can be beneficial for human-robot collaboration due to the low collision energies. Because of the parallel leg chains, the risk of collision and clamping increases. Shown are different contact situations: collisions at the mobile platform and at the kinematic leg chains, such as the first or second link, clamping between two links of a leg chain. The detection of the contact and the strategy represent a research gap within the human-robot collaboration with parallel robots. The main point of this work is the addressing of contacts on the robot structure. The point with coordinates xc represented by the joint angles is considered. The differential kinematics of this point includes the contact Jacobian matrices, via which the relation between the contact point velocities and the platform as well as the joint velocities can be established. By projecting the forces measured by a force torque sensor onto the joint coordinates of a real parallel robot, it is possible to determine the motor torque constants. This is important because too low or too high values would lead to a bias of the model-based force estimation and thus an increase of false positive or false negative contact detections. Furthermore, the control with low impedances and the accuracy of model-based force estimators will be investigated. Finally, detection and reaction of collisions and clamping are demonstrated. Motor torque constants are identified by applying forces to the force torque sensor in a robot configuration. The kinetostatic projection allows to determine the linear relationship between the projected torques and the measured motor currents. Validation is performed in a different configuration by comparing the disturbance observer's estimate of the generalized momentum with the projected measurements. A Cartesian impedance control is used for contact stiffness. Due to the direct drives, low impedances can be parameterized. The estimate of the disturbance observer deviates from the measurement by only up to 5 Newton. Based on the observed forces, contacts are detected, after which the robot switches to the zero-G mode. The disturbance observer of the generalized momentum is compared with the Kalman filter as well as a sliding mode approach in terms of accuracy and detection time. Within 10 milliseconds, the contacts are at a velocity of minus 0.9 meter per second are detected. Contact forces on the robot links are also measured and transformed by a kinetostatic model. The use of model-based force estimation for contact detection and response at higher velocities is also demonstrated for clamping at the leg chain. In summary, it is demonstrated on a real parallel robot how the kinetostatic projection can be used to identify the torque constant, to investigate the low impedance and the model-based force estimation, as well as to realize a collision and clamping detection together with the reaction in the form of a change to the zero-G mode.